What's up, guys? I'm going to look at the Orbital Motion Lab interactive from about a week ago. And so with this, we talked about it in class, but I know some of you probably need a little more time. But this is the key stuff that I want to make sure you understand. So with doing this, the first part asked about the object's velocity, and then the magnitude of that, or the amount, and then the direction. And then the second part asked about the net force. So let's look at those here together. So if I've got the object here and I put on the velocity vector and I start it, you can see the velocity go in this direction. If it goes, slows down, and then as you watch as it comes back this way, it speeds up. And at all points here, if I were to pause it, here's what we spent a lot of time in class talking about, and you should be comfortable with describing the direction of this as tangent to the path. So as it's going there, the velocity is always tangent to the path. So we'll type that in a second, but the velocity increases till it gets here, and then it starts decreasing till it gets here. We put the force on there. You can see the force as it gets to this side, the smallest vector. Now the force is going to start increasing in size as it gets closer to the object that it's orbiting. Pretty laggy today, huh? So those are the kind of the key things. And if you need a better look at that, you can always go into the assignment and make sure that you can see it. So the magnitude, how that changes as it orbits, we would say that it is highest when closest to the object it's orbiting, and decreases as it moves away, and then increases as it moves towards. And then the direction of this is always tangent to the path it's following. So if it were to suddenly go out of orbit, it would move in a straight line away from that. And then the net force here, so the magnitude, it's largest when closest. So same pattern there as the velocity, and smallest when farthest away. And that would stem from you guys knowing gravitational force is inversely squared relationship with gravitational force and distance. So what direction is the net force as it moves through the orbit? It's always towards the object it's orbiting. So they're different, very different from the velocity, which is always tangent. The force is always towards the object it's orbiting, and that is because it's the result of the gravitational force. So some people struggle with realizing that part of it. So you want to make sure you put that in there. Now here, if you increase the eccentricity of the orbit, describe that effect. So we can do that. Maybe let's make this a little bit bigger. Since I've got this going, if I were to increase the eccentricity, so that made it go from this outside ellipse to this a smaller height, if we would call that height, but a more of an elliptical shape. And I like what this does. You can actually see that slingshot effect that we talk about as it does this in this kind of an orbit. So increasing the eccentricity, it just makes it more elliptical shape. Probably the easiest way to describe that. And then what's going to result in a circular orbit the eccentricity of 0. So when you change that to bring this all the way down to 0, that puts those two foci of the ellipse together, and then makes it. Let's reset this so get that stuff out of the way. Then you can see here it just becomes a circular orbit. And then we had to look at the velocity and force. So we're looking at that now. You can see that in the circular orbit, velocity doesn't change, force doesn't change in magnitude, and that means the amount. The direction does change, so that'll be a key thing with something we're going to do later this week. But as we go back to this, so it talks about the two differences there, and so elliptical orbit versus a circular orbit, the magnitude of the velocity, so that's how much it is. That changes in an elliptical orbit, but is constant in a circular orbit. Difference in net force, so it's really the same thing. So the magnitude changes, but in an elliptical orbit, but not in a circular orbit. So that's a key difference between those things. So if you had to do a drawing where you put in the vectors, you should be able to think right now, like, oh, okay, would I be able to do that? Could you comfortably put in velocity vectors and force vectors on those two different orbits and make them relative to each other? So here, for elliptical orbits, the direction of the velocity of the satellite is always, seldom, or never perpendicular to the net force. So this was seldom because it was really at the two ends, or the two sides, I guess I should say. So we'll bold that. And if you want confirmation on that, just go back and look at that and right at the two sides here. If it's going this direction, that's where they were perpendicular. And but in a circular orbit, those are always perpendicular, the net force and velocity. And you can see as this thing goes around, those are always perpendicular to each other. So, hold that for you. And then here, this paragraph I thought was hard for a lot of kids, but we talked about it in class a lot and did an example. So the satellite is orbiting the Earth in elliptical motion. It'll move, so here when it's closest to the Earth, it moves the fastest. And we've talked about some other reasons why that depends on. And while moving towards the Earth from D to A, so if we go back to this and reset it, it moves like this. So now it's moving towards the Earth, right here. And so the D to A reference comes from this part right here. As it moves from D to A, there's a component of force in the same direction. So that force, as we play this a little bit, so here's where we talked with vectors in class, but now as it's moving here, so I'm going to let it get about to this spot's good. So it's moving this way, force is this way. So you'd think, oh, those aren't really in the same direction, but there would be if we broke this force vector into its components. Part of it would be along the same, they're in the same direction as this. So that's what that's kind of referencing. So those would be in the same direction, and that's what causes it to speed up. While moving away from the Earth, there's a component of force in the opposite direction, and that's what causes it to slow down. Why there's a big space in there, but let's get to that. So that's what's going on there. So you should be able to think, well, why does it speed up and slow down? And it's because there's a component of force, either with it or against it. Close this. All right, so then we took a look at this other simulation. And so the first thing we had to do was talk about what was true about the force vector on the planet when compared to the star. So let's take a look at that. So we're going to put these on, and it says, well, here's the force vectors right here in the planet and the star, and this gives you a great look at those being the same. We talked about why that is, but you should have an understanding of that. So these are the same size. And why is that? So some people would say Newton's third law, which is true. Okay, that's a basic explanation of it. And so they're pulling equal and opposite with equal and opposite forces. So, and a good way to think about this is if you think about that gravitational force equation, nothing would be different if I did it from the star to the planet. They'd be the exact same. So that's kind of the key thing. So now this is going around. I'm going to turn gravity off, and you'll notice, and what I like about this, let's pause this. Where's the reset? Oops, I can't get to the reset button on this because it's behind my screen, so that's not good. Let's see, we'll do this. We'll refresh then. So I'm going to just leave velocity on. This is why I want you to see it. As it gets here, I'm going to wait till it gets about to the top, and boom. So that's where that tangential velocity becomes pretty key. I can move that. So it's just going to follow along in a straight line once I take gravity off. So here the planet flies away because there's no force keeping it in orbit. So most of you guys did okay with that. You're fine with that. So increase the mass of the sun. What happens to the Earth? Decrease the mass of the sun. So let's take a look at this. So mass of the sun, we'll just put it at 1.5. Boom. What happens? Let's look at the path here. So that changes us into more of an elliptical orbit. Right there. And then if we were to decrease the mass of the sun, uh-oh, he's out of here. So return it. Now I think what some kids did is they did these while it was moving. So that's a little different. So to take it here, now if I just go, boom, that puts it on a little different path because it already had been going. And then here we've got it coming towards, and let's, boom, bye-bye. So go back to this. So increase the mass of the sun, more attraction, and changes the orbit to an ellipse. And if I decrease the mass of the sun, then it was not enough attraction, and the planet flew away. Increase the mass of the Earth, drop the mass of the sun. So let's take a look at that. So we reset this. Mass of the sun less, mass of the Earth more. So you might think, oh, it should be, nothing should change. So it just goes